Alright, in this video I'm going to be talking to you about exact equations. But before I want to start, I want to kind of take it back to AP Calculus for a second and look at something like this. This is a task we were able to do last year, right? We were able to look at an implicitly defined curve and find dy dx, right? Just by taking the derivative of everything with respect to x. So we would have had something, like 3x squared plus 3y squared dy dx plus, and then I'd need to use the product rule, right? I'd take the derivative of this thing with respect to x, and that would be 2, and I'd leave that thing the same. And then I would leave this the same and take the derivative of sine y with respect to x, which would be cosine y dy dx. So 2x cosine y dy dx, and then that would be equal to 0. And then what we did was, if we wanted to find dy dx in terms of x and y, was we collected everything that had dy dx on the one side of the equation, pushed everything else to the other side of the equation, factored out the dy dx, and then solved for it by dividing. Right? It worked the same way every time. So we had eventually that dy dx was equal to, all right, get rid of everything that didn't have a dy dx on it, so that would be negative 3x squared minus 2 sine y. And then we would divide it by everything that had a dy dx on it, so it would be 3y squared plus 2x cosine y. So 3y squared plus 2x cosine y. Okay, so the question today is, what if we ran into this, right? What if we ran into a dy dx equals some kind of bad fraction, and its solution was the type of curve? I mean, I don't really know what the graph of this thing looks like. It might self-intersect, it might not be a proper function. But either way, this is the type of thing we have no hope of solving for y on its own, right? And now there will be some of these where we can eventually, if we try hard enough, we can solve for y and get an explicit y equals some function of t solution. But for the most part, we're going to be looking at places where we're going to be okay with settling with an implicit solution. Okay, so, and if we kind of start with that mentality that, okay, wait a second, maybe our solution, we're not going to be able to solve for y in terms of t, but we will be able to maybe get an implicit equation for it, and that could be maybe just as good. That can kind of open up some things that we can, some differential equations we can solve. So I think what I want to do is I want to solve this one for you kind of in general first, and then I'll do a couple of examples. All right, so suppose we've got, some kind of expression in terms of t and y without y primes. And then we've got, some expressions that have a y prime attached to them. And maybe we were able to factor out the y prime, and we set that equal to 0. This is going to be kind of the situation that we're looking at today. Okay, this has a number of different forms, but hopefully I can just, when I do the example, I'll show you what that might look like. And suppose that we're going to be shooting for an implicit solution. Now, an implicit solution is where I've got just x's and y's freely mingling together. We've also seen that when we are, accepting that maybe a function could take in two variables. So, suppose that this equation f of t and y, which equals some constant, is an equation that satisfies this. Okay. I need to remind you of the multivariable chain rule. Okay. So let's just talk about a function. I'll switch it up to g. Okay, so if g is a function of x and y, and x and y become functions of t, that was the multivariable chain. G of x and y. Where really x was x of t and y was y of t. Well, what that was the partial of g with respect to x times the derivative of x with respect to t, so dx dt plus the partial derivative of g with respect to y times dy dt. Now, this is a little bit of a symbolic trickery here, but I'm interested in the situation where y is a function of x, right? So if y is a function of x, if it's like y of x and x of x, well then dx that's just 1. Okay. Now, I am specifically in this situation, I'm actually interested in g of t and y, right? F of t and y, which is equal to some constant where y is a function of t. Okay? So what I'm going to say is that the derivative with respect to t of g of t and y of t, in the exact same way, it's going to be, pardon me, x is now t. So it's going to be gt times dt dt, which is going to be 1, plus gy times dy dt, which I'm calling y prime. Okay, so what I'm saying is, if there is some implicit solution out here that we're going to view as a function of two variables equal to a constant, which is of course the level curve of a surface in space, then it will be the case that, well, what we're really looking at is f's partial with respect to t plus f's partial with respect to y times y prime. Well, I feel like I had something, I feel like I was very close to making a point there, and I kind of lost myself. I'm going to pause for a second, regather my thoughts. So specifically where I'm at right now is I'm going to say, therefore, m is equal to the partial of this f with respect to t. Yes. And wait. Partial of f with respect to t. I think I said it. Okay, I didn't. Okay, m is the partial of f with respect to t, and n is going to be the partial of f with respect to y. Okay. Now I'm going to erase this because I need to say something else. Yeah, because now I'm arriving at my point. And if this is the case, then we're going to need my to equal nt because of the equality of the mixed partials. Okay. So, the Clairaut theorem, the mixed partials, my is going to be fty, and nt will be fyt. And so in order for this to work, I need for these to be the same. I need my mixed partials to be equal. And so I'm going to say, now I need my equals nt. And this should feel familiar, right? Especially if you just finished, kind of going through my short course in vector analysis. Right? There was lots of times where we were interested in the partial of this m thing with respect to y being the partial of n with respect to x. That was when a vector field was conservative, and we were going to be able to bump up and find a potential function. And that's actually exactly what we're going to do here, okay? Because if we want to find f, we can find it by taking the antiderivative of m with respect to t, and by taking the antiderivative of n with respect to y. So, kind of like the solution here is that this f is actually the potential function for the vector field that's like, has first component given by m and second component given by n. And how that connects to the differential equation m plus ny prime equals 0, I don't exactly see right now, and I don't think it would be worth me spending a whole bunch of time trying to run down. But I'm sure there is some connection there, right, that I'm just not seeing. Oftentimes having to work on this by myself, So, what else was I going to say? Oh, yeah, and so in conclusion, this f of x and y is going to be equal to, well, the antiderivative of m with respect to t, but it's also equal to the antiderivative of n with respect to y. And so I think now would be probably a good time for me to do an example. All right, so I've got, let's see, this is written very small. I've got y prime equaling hold on, I'm going to write this a different way because I've seen this in a couple of textbooks written in kind of like a differential form, and I just want to make you aware that this is actually the same thing, and I don't have to write it as y prime equals some fraction that I'm going to then distribute and get into this. It might look a little different, so let me just kind of mentally work this around. All right, yeah, so sometimes you'll see it written like this in kind of like a differential form where, 2ty minus 9t squared dt plus something else dy is equal to 0. And of course, the first step is just going to be divide everything by dt and say, okay, well, 2ty minus 9t squared plus that thing dy dt is equal to 0. Well, 0 divided by dt. Probably going to be 0 if we can even divide both sides of an equation by dt, which I'm saying we can. So, what was I going to say? Oh, yeah. 2y plus t squared plus 1 times dy dt is equal to 0. And this is kind of looking like this form where I've kind of considered this already, right? So, this is going to be solvable using this technique if my is equal to nt. Okay. Well, the partial derivative of the first thing with respect to y is going to be, well, 2t. And then over here, the partial derivative of n with respect to t is going to be 0 plus 2t plus 0. And so I see that I've got these two partials are the same, and that means my equations are exact. That's kind of like the terminology, is that, and I didn't, define it, but if you have a differential equation like that, and my is equal to nt, then your equations are exact, and you can apply the solution. Okay. Now, it's pretty much over now that we, know what we're looking for and what to expect, because I know that the solution is going to be some kind of curve. F of t and y is equal to c. That's what I'm going for. Okay. But I know that f is going to be the antiderivative of this with respect to t. So I can say f equals, let's see, the antiderivative of 2ty minus 9t squared with respect to t, which is going to be equal to, okay, with respect to t, that would be t squared y plus negative 3t to the 3. And then there could be some kind of like other hanging on function of y. All right, and then hopefully I'll just discover that, when I anti-differentiate the other part. You remember how this went. Okay, so f is also equal to the antiderivative of, where is it, 2y plus t squared plus 1 with respect to y, which is going to be y squared plus t squared y plus another y, maybe plus some constant function of t. And maybe just to be extra clear, I'll call them C1 and C2 because they are potentially different. Okay, C1 of y to me is looking like, hold on just a second, let me grab some color. Usual colors are, but at least we'll do. All right, so for my constant function of y, I can find it, it's down here, it's this y squared plus y. Okay. And then for my constant function of t, let's see, it's up there, right? Yeah, negative 3t to the 3. All right, So the function that, or the, kind of, I don't really want to call it a function, right? Because it's the level curve of a two-variable function. But the expression that I'm looking for, this f, is going to be equal to, say, y squared plus t squared y plus y minus 3t, right? It's got all of these things once I merge them. Okay? And I'm going to say, well, what I'm really looking for is y squared plus t squared y plus y minus 3t squared is equal to some constant. And now I didn't really give you an initial condition, but suppose I did. Let me just make one up real quick. How about 0, -3? Maybe, I'm not sure. And then I'll say that y of 0 equals -3. And then this actually should be very easy to find my value of c, because I'm just going to plug in on t and y and get myself a number. So y is -3, so this will be 9. Plus 0 plus y is -3 minus 0 equals c. That looks to me like c is 6, right? Okay, so I can conclude if I want an implicit solution, yes, I actually like this one because I can go even farther with it. So if I want my implicit solution, it's going to be y squared plus t squared, wait, no, I actually like the way it's written. And that's equal to 6. Okay? And if we're looking for an implicit solution, this is a perfectly safe place to stop, right? Now, this one, it doesn't look like it, but this is something I can solve it for y in terms of t. And you know how to do it, you just may not have ever considered doing this before. So what I'm going to do is I'm going to actually clear this discussion off, and I'm going to show you how to solve for y as a function of t. And then I think that'll be probably all for this video, because I don't want to do, just a whole bunch of examples, because they do end up working pretty similarly, provided that the equations are exact, right? If my equals nt, we're going to kind of observe the same process, and it's just going to work the same way. Now in the next video, I'll have kind of an alternative for you in case you run into one that's like, close to exact, but not quite, and you feel like maybe if I just adjusted it a little bit, I could make it exact. That's a technique, that's probably the next technique we'll look at. All right, so over here, suppose you're looking at y squared plus t squared y, but you have t squared y plus another y is something that I could write as t squared plus 1y. And then plus a -3t squared minus 6, and that's 0. Maybe you're saying it at this point, maybe you're not. This is quadratic in y. We've got a quadratic formula, right? If we've got, ay squared plus by plus c is equal to 0, then we can solve for y in terms of a, b, and c. Well, nobody ever said that a, b, and c couldn't themselves be a function of t, right? So I'm going to say that y equals -t squared plus 1 plus or minus the square root of b squared, oh my, this could be rough, minus 4 times a, well at least a is 1, right? 4 times a times that, all divided by 2a, but that's just 2 times 1. And there's more analysis that I can do here, right? I can definitely go off and expand, wait. No, it's that thing that needed to be squared. Okay, so I could run this through, right? I could figure out what this is going to be a 4th degree polynomial in t. I could go and graph this thing using technology and find, a suitable domain for a solution, right? Because you know that more than likely a 4th degree polynomial is going to have at least some kind of region where it's negative, and that would not, this would not be a valid solution in a place where the square root was negative, or the radicand was negative. And then, you know, for our particular solution that y of 0 was equal to -3, it's either going to be the plus or the minus. And maybe I can go through and show you that analysis. I don't think I want to, I think I'd need technology to go in and find the actual domain of the solution curve. And even then, you know, being a 4th degree, it probably wouldn't be in terms of nice numbers anyway. So no sense in going that far. But I can show you how to determine whether it's the plus or the minus, right? Because -3 is equal to the negative of t squared plus 1, which is 1, over 2, and I think that that is going to need to be a minus, right? Because I need this to be -6 over 2. So it's going to be minus that square root, which, you know, presumably 1 minus 1 plus 24 is 25. Yeah, there it is. -1 minus 5 divided by 2 is -3. Okay, minus that square root of, turned out it was 25. So, you know, I can conclude that at least on whatever domain that this thing is defined on, the particular solution to that differential equation is going to be y of t is equal to, you know, the negative of t squared plus 1 minus that square root of t squared plus 1 squared minus 4 times that. Negative 3t squared. All divided by 2. And that is the technique of exact equations.